Hello again, physicists. Today's installment, I will be showing you how to determine the net force acting on an object. So let's get started. First step, if you're going to determine the net force acting on an object, you need to draw a free body diagram, since the free body diagram will show us all of the forces acting on that object. Make sure that if you have forces that are not lining up with your coordinate system, that you break those forces into their components first. After you have done that and your free body diagram is clearly showing how all of the different force vectors will line up on your object, you need to consider what direction may the object accelerate in. After doing that, now you will add the forces that are lining up in that aforementioned direction from step 2, while taking into account your coordinate system. If a force is pointing in the negative x direction, then that means it will subtract from a force that's pointing in the positive x direction. So just keep track. Your coordinate system is there for a reason. It's to help you figure out what forces will add together, what forces will subtract from one another as I determine my net force. Let's now look at an example where we're going to determine what the net force is acting on an object. Keep in mind, I'm not going to give you specific numbers here. Instead, we're going to be operating using symbols instead. On the AP Physics 1 exam, very rarely will you be working with specific numbers. A lot of your solutions will be algebraic solutions. So our example will have a sled being pulled by a rope at an angle of theta. And as a side note, we're going to consider that this surface is frictionless. So this means that we will not need to worry about friction at all. No friction. So the first thing is I need to draw my free body diagram. In this case, I'm going to have to give my coordinate system. So up will be the positive y direction, and to the right will be the positive x direction. Now I know my system will be the sled. So let's draw all the forces that are acting on the sled. Right off the bat, we can say, well, that sled is on Earth. It is subject to the gravitational force of the Earth. So we'll draw in FG. We have the surface, the snow, pushing back up on the sled. That would be a normal force, Fn. And the last force we would need to include is the force of the rope pulling on the sled. That would be Fa. And I'm just going to make a note that it's being pulled at an angle. Most of the time, those angles will be referenced from the positive x-axis. So there's theta. Now here's the problem. I can't really tell what my net force will look like because I have a force that is not lining up with my coordinate system. I'm talking about my applied force here. It's not pointing strictly in the positive x-axis, and it's not pointing strictly in the positive y-axis. It's doing a combination of the two. So I need to take Fa and I need to break it down into its components so that I have one piece pointing in the y direction and a second piece pointing just in the x direction. So I'm going to rewrite my free body diagram. Nothing will change about the gravitational force or the normal force for that matter. But now if I break this vector into its components, my applied force, my x component will be pointing to the right. And if I used SOHCAHTOA to figure out what that x component would be in terms of Fa and theta, I would find out that it is Fa times the cosine of theta. Cosine, there we go. And my y component would be pointing up, and SOHCAHTOA would tell me that my y component would be Fa times the sine of theta. Sine, there it is. Very well. Now I can see very clearly how my forces are going to either add or subtract with one another. For example, the net force in the y direction. It's going to be equal to, and I'm going to use my coordinate system to help me out, the normal force and Fa sine theta, the y component of my applied force, are both pointing in the positive y direction. Therefore, they're going to stay positive as I add up the forces in the y direction. So I'll have Fn plus Fa sine theta and then the only other force pointing in the y direction is the gravitational force. Since it's pointing in the negative y direction, that means I'm going to subtract it. So it'll be minus Fg. So there's a complete representation of my net force in terms of all forces acting in the y direction at least. Now I need to also consider the x direction and if I have a net force in the x direction. So to do that, I would look at my forces acting in the x direction, and I would see I only have one. It is the x component of my applied force. So here's what this ultimately means. All it means is that I can say for a fact that I do have a net force in the x direction because I only have a single force in the x direction. There are no other forces to balance it out and give me zero net force in the x direction. In the y direction, it's not as clear as to what's going on because I have three forces at work here. Two that are pointing up, one that is pointing down. In the case if all of these forces added up to 0, it would mean I would have no net force in the y direction, therefore I would not be accelerating in the y direction. If for some reason the normal force and the y component of my applied force exceeded the gravitational force, then I would be accelerating in the positive y direction. Vice versa, if the gravitational force was larger than those other two forces up here, I would be accelerating in the negative y direction. So the result of that sum, that net force you get, again will tell you what direction your object is accelerating in, or if your object is even accelerating to begin with. All right, as a second example, we're going to draw a free body diagram and determine a net force for a book being pushed horizontally across a table. And in this case, we are accounting for friction. So I have my coordinate system. I'm using my standard coordinate system with the positive y and x axes being to the up and right directions respectively. My system will be the book. And now I need to identify and label the external forces that are acting on this book. So let's start with the most obvious one. That's right, the force due to gravity. It's still there, pointing down. Since it's resting on a table, we will have the normal force of the table pushing back up on the block. And then we know that we're pushing it across the table. It wasn't really specified what direction we were pushing it in. I'm just going to say that it was being pushed to the right, so our applied force will point to the right. And since there is friction, remember friction will always try to oppose the motion intended for the object. So if I'm applying a force to the right, it means I'm trying to move my object to the right. Therefore, friction will work against that, and friction will act towards the left. We'll label that FF. And now from here, I can figure out, well, will I have a net force in the y direction, or will I have a net force in the x direction? So for the y direction, again, I'm looking at how do the forces in the y direction on my free body diagram add or subtract. In this case, it looks like that the normal force is pointing in the positive y direction, so I'll keep it positive. And the gravitational force is pointing in the negative y direction, so I would subtract it from my normal force. for the x direction, I have an applied force that is pointing in the positive x direction and a frictional force that is pointing in the negative x direction. And since it's pointing in the negative x direction, I would subtract that force of friction from my applied force. So here are two expressions representing the net force in the y and in the x direction. The last thing I'm going to do is talk about the potential consequences of these net forces. So let's say that we had numbers for the normal force and the gravitational force, and it came out to be 0. And the same thing was true for the applied force and the frictional forces. In other words, both of these came out to 0. Well, it would tell me a few things. Number one, probably most obviously, that there is no net force at all acting on this object. But what it really tells me is it tells me something about the state of motion for my object. Because keep in mind, only a net force will cause an object to accelerate. So if there is no net force acting on the object, it means there is no acceleration. There are really only two cases of motion where there is no acceleration. Either the object is at rest, or it's moving at a constant velocity. Oh, come on. There we go. Constant velocity. So if we looked at this particular object and we were told that it is at rest or that it is moving at a constant velocity, in this case, since we're saying the book is being pushed horizontally across the table, it's implied that it is moving. If we said it was moving at a constant velocity, we would be able to automatically say then that the normal force minus the gravitational force would have to be equal to 0, and also that whatever the applied force is minus the frictional force the book experiences, that also must be equal to 0. This is a specific instance called equilibrium, where you have no net force, therefore the object is at rest or moving at a constant velocity. And we will deal further with equilibrium in class. That's plenty for tonight, so make sure that you get your notes down, ask any questions that you may have for class tomorrow, and until next time, physicists, until next time.